It's done now.
Okay, so as I was saying, this work already started when I was in Scotland, and the work I want to present you today is about formal verification of higher order probabilistic programs. It's a work that we presented now almost 2 years ago at Popol, so it's not my most recent work, but I thought this would fit well the topic of your grant, and also is something we are still working on, we are still interested on, and so I thought it could be a good topic, also because some of the experts in the field are in Scotland. So I should say also this is mainly the work of Tetsuya Sato, who was a postdoc with me. So he is the one that really developed what I will talk about, and this is also the result of a collaboration with other people that you see listed here. Okay. All right, so just a quick outline of my talk. I will give you some motivations that mainly come from some work we have been doing on privacy preserving data analysis, and in particular, some of the motivation come from privacy preserving machine learning. And then I will show you mainly a framework that we design, which is built on a domain-specific assertion logic, but it consists of a unary and relational type system. Two type system, a unary one and a relational one, and so I will go a bit in detail into that. And then I will try to conclude. So I'm sure I don't need to justify the importance of machine learning application today. I think you know them as well as I do. We have application in different fields like autonomous car, image recognition, in automated translation and so on. And it's important, as I believe, as verification or programming language people to look into this novel application and try to understand what we can do for this field. Now, when I look into this field, when we look into this field, what come out straight is that most of these application requires some probabilistic reasoning, and I'm not the first to argue in the community that we need to focus more on probabilistic program. There has been a lot of work starting in the 80s on probabilistic programming, and much of renewed attention came up about 10 years ago in connection with machine learning. So I think nowadays probabilistic programs are considered an important object of study in our community. Now, one more specific question is which properties do this program need to satisfy? So as I would define myself as a programming language researcher more than a verification researcher, but if we put our hat of verification, usually we are interested in soundness of our program or correctness of our program. And often correctness for standard deterministic programs is something that our community know pretty well, is easy or relatively easy to define when our program is correct, when we have a bug. For probabilistic program, the thing become a bit more subtle in the sense that what we can do by looking at the program is not often what we want to say for the application we have in mind, like in the case of machine learning application. So let me try to give you what I think we should say as a property about this program. So an example, as an example, I can take a Monte Carlo approximation. So with the idea of Monte Carlo approximation is pretty simple. We want to approximate the expectation of some function, h. And what we do, we sample a finite number of data, and then we apply h to this data, and we just take the empirical expected value, and then we can analyze this result. Now, here I'm using, of course, Monte Carlo in the most general way. Then there are many different Monte Carlo processes. There are many different algorithms. So I don't want to go into this discussion. I'm just consider the Monte Carlo process in general. And we can try to implement this with a program like the one I show here on the left. Let's see if I can. Okay, you don't see my mouse, I imagine. I don't see it either. So it's okay. So here on the left, we have a program which mainly represents the Monte Carlo example I gave you before. So it's a recursive program which take a function h and sample some values, and then try to from a distribution, and then try to compute the empirical expected value. Now, the property that we want to guarantee for this program, the correctness property we want to guarantee for this program, is something like what I wrote in the purple box. So in this case, for example, we want to show that the probability that the value that we obtain is not too far, or the probability that the value z that we obtain is farther from the true expected value of h for a constant epsilon is bound by what you see on the right. So this sigma square over epsilon n square. Now, what are these parameters? So these are the sample size, so how many samples we take. Epsilon is some constant that we use to say how far they are, and sigma square is the variance of the variance of the distribution processed by h. So we don't need really to look at the specific statement. What I want to communicate here is that the kind of soundness or correctness that we are interested in is essentially probabilistic and quantitative. So we want really to reason about this kind of statement. And you will see a bunch of this statement in all along my talk. So another property, for instance, based on the same language that we may want to show, is that suppose that we are interested now in computing the expected values of two functions, and h and k. You see the one for h on the left and k on the right. Of course, since they are bound, these are exactly the same function, but let's imagine that we pass them two different functions, h and k. Now, what we may be interested in understanding is how these two functions compare. In particular, we can compare them through a statement, again, similar to the one we saw before, not exactly the same, that you see now in the gold box. These statements say that if the expectation of the two functions is far apart enough, then we can show a bound on the probability of getting two values from the Monte Carlo sample. We can mainly provide some confidence interval for how much these two samples would be apart. Okay, so again here we have some probabilistic and quantitative statement that we want to reason about. So in some sense, the main point I want to draw here is that reasoning about probabilistic program for application like we need in machine learning often end up having this kind of general shape where we have a quantitative and a probabilistic statement. Okay. Yes, yes, the two are bound, so they are exactly the same function, but I was just suggesting we think about them as two different, passing their two different functions. Okay, so, but as I said, my main motivation actually comes from private preserving machine learning, where we are interested in preserving, while we do analysis, also preserving the privacy of individuals, that contribute their data. And I spent quite a lot of time to work on a notion of privacy, which is called differential privacy, which is a rather simple idea, is the idea of adding some randomness to a data analysis in some way. For instance, adding noise to the answer of the data analysis so that the noise can protect the individual record in a data set. Now, in this setting, I will not go too much into this, although I will show you the definition, but there is a trade-off between privacy and utility, because if I add too much noise, then I protect very much the result, but I make the result, I protect very much the user, but I make the result useless. If instead I add too little noise, we have a useful result, but we can compromise privacy. So this was actually the idea that some researcher tried to study and came up with this notion of differential privacy, which I show you here, but I will not use really in the rest of my talk, since it's just a motivation, not really something we will use technically. But in general, this definition say that a probabilistic program, you can think about Q as a probabilistic program, is differentially private for some parameter epsilon delta. If when we take two data sets that differ in one individual, the probability of seeing some result in the two running the program on the two databases, the two data sets, are close. Where by close, we use this equation that you see here. Now, the real interest for me connected to this talk for differential privacy is how we reason about accuracy of privacy preserving analysis. Again, we use a statement that are very similar to the one I showed you before. So in general, we are interested in saying that if we run a differentially private data analysis, PQ, on some data set D, then the probability that we get something close to the analysis that we would have without noise, this little q over D, little q for D, is bounded by some beta, and we are looking at how far this true answer and the noise answer are, and we quantify this by alpha. So these are kind of statement that we have everywhere in differential privacy. And actually, there is another form of similar statement that we have where the probability does not depend only on the probabilistic program, but depends also on the data. Okay. Now, these are two essentially different way of measuring accuracy in differential privacy. They are essentially different because in one, we can use the randomness from the data, in the other we don't. So in particular, you can think that in one, we are looking at the difference between the result of a probabilistic program, which adds some noise, and the result of running the probabilistic program without noise. So if we fix the randomness, over the data set. So we are looking at two specific points over the same data set, two specific process on the data set. The second one is instead with respect to the population. You can think about this Matcal P. I don't know if it is a Matcal, but this P here as the population. So we are looking at how well perform our program with respect, how well our analysis perform with respect to how it would perform on the population, so not on the specific data set. And these are essentially quantitative different properties. Now, let me skip this because I think I already gave enough motivation. Part of our motivation comes also from the fact that usually these statements are useful also to guarantee privacy, but it's not essential for my talk. Maybe one other essential point that I want to say is that the process of generating data under this private machine learning is often quite involved, and you should not think only about, oh, I computed data analysis and I add noise, because one of the classical problem, for instance, is how to release a whole data set in a synthetic way so that is protected by privacy. So, for example, this is a classical application that people are looking into for a machine learning task. So in particular, this has been developed actually in the learning theory community quite a lot. Now, oops, sorry, I'm going in the wrong direction. The last motivation I want to say is that if we think about releasing data, then we can also think about releasing the process to generate data. And this can be done by releasing, for instance, a Bayesian network that describe the generating process of our data. And we can guarantee that this Bayesian network guarantees differential privacy. So we have been working on this, and again, we have a statement of correctness like the one I showed you before. Okay. All right, I think this is enough for motivation. I hope I motivated you into thinking about correctness of probabilistic program in a more general sense, where we think about correctness in terms of statement, probabilistic statement, probabilistic and quantitative statement. But now, how can we reason about all this property, and also for different programming model? Because if we think about the Bayesian network is different from thinking about just releasing our data. So how can we do this? And this will be the rest of my talk. So but actually, before moving on, is there any question on my motivation? The kind of statement I'm interested into? All right.
Just to say, Marco, seems all clear. So we'll
sure.
completely buy your motivation. See where you're coming from.
Okay, good. All right, so how can we reason about this property and for different programming model? The tool that we use is a classical tool from programming languages, is program logic. So in particular, we want to reason about precondition, program, and postcondition. Now, in particular, we are also interested in relational property, and so we also will use relational thinking, where relational thinking you can just think as very similar to what I said before, reasoning about precondition, program, and postcondition, except that now we have two programs You can think also about the case where these two programs are the same as a special case. Because what we are really interested is about the relation over the input and the relation over the output. So this is what make a bit the difference. If you think about the example I gave you before, a property we may be interested to reason about just in a unary way. I will say unary when we consider only one program, is about how far is the expectation, how far is the result of Monte Carlo from the true expectation of the function, while a relational property is how far are two result of two run of Monte Carlo in two different functions. Now, how do we implement this kind of reasoning? We propose a three-tier type system or logic. Actually, we use the word framework because some people like to think about it as a program logic. Some people like to think about it as a type system. So we just call it framework. This framework has a three layers. So the bottom layer is a logic for reasoning about expected values and Bayesian update, and is semantically based on quasi-Borel spaces. I see that Hoad was around, so quasi-Borel spaces is a semantics for a probabilistic program that Hoad and many others have developed, and we use their work to as a foundation of our work. On top of this, we use a unary system, which has specific rules for probabilities and Bayesian update, and on top of this, a relational system with, again, similar specific rules. Now, I didn't say what is our language, but here it is. So now I will start to go a bit more in the technical detail without I will not try to go too much into technical detail, but let's try to see some of the details. So our language is a PCF-like language, enriched with monadic construction for probabilities, and you see them. It would be great if I could point, but it doesn't seem I'm able to. So the two monadic construction are the one in the second row of the grammar, return E and bind E and E1. Bind E and D. And then we have some basic operator for continuous distribution. In particular, you can see again in the second row of the grammar, we have uniform, Bernoulli, and Gauss. And then we have this construction that we call query, which is written as query E, and then this right arrow E, which is used for conditioning. The rest for conditioning or for reasoning about probabilistic update or Bayesian update. Now, the rest of the language is a kind of standard PCF-like language over real numbers. Now, again, types reflect this distinction between monadic types and basic types, but in particular, we distinguish also between base types and regular types, where we have monadic types, arrow types, product types, and list types. But for the talk, I think you can just think about types in general. And we assume in general to have the terms are well typed in a simple type manner, where you can think about it as mainly a somehow trivial extension of PCF, where you give a monadic type to distributions, and to the component like a return and bind, you give the classic monadic types. One additional requirement that we have is termination. We require our program to be terminating, although proving termination is somehow orthogonal to our reasoning, so we will just assume that there is a way to prove termination. Now let's see some examples of what we may want to do with this language and what are the different components that we have. So in general, we may want to create a more complex distribution. So for instance, we may have a sample from two distribution, and then we may want to return their product distribution. We can do this simply by using our bind construction and build the pair of a pair of points representing the product distribution. Now, what we will use often, what we use in example often is a kind of do notation. I'm sure you are all familiar with Haskell and do notation. So here we use a similar kind of notation where we use this mlet to denote the monadic composition. So in this program, we sample X from a Gaussian 0,1, we sample Y from a Gaussian 0,1, and then we return X and Y, and this will provide us a product distribution representing the product distribution of the two input distribution. Now, a more interesting construction, this is quite standard if you think about probabilistic program. A less standard construction is conditioning, although, as I said, in the last 10 years, probably has become more than standard, which is the idea of working with a conditional distribution, and which you can think about as a kind of way to filtering a probability distribution with some conditions. So here an example, suppose that we have the probability distribution on the left, this blue Gaussian, and then we have the condition X greater than 0. Then we can filter out the input distribution with this condition. Mainly, the condition represents some kind of a likelihood function. Now, an important point when we think, one way to describe this in our grammar is through this construction query that takes two parameters. The first one is a probability distribution, and the second one is the likelihood function. And so what it does, the semantics of this program is to filter out the distribution and rescaling it accordingly. So an important point in this conditioning is rescaling. So the result distribution is still a distribution. So after filtering, we need to rescale our result. Here is an example. Suppose that we have a distribution like you see on the left, on the top left, which assign 1/4 probability to these spaces. And now we want to condition it with the condition you see on the right, so that X and Y are less than 1/2. What we obtain is something like on the bottom of my screen, where we have the support is just the one in that respect the condition, but now we need to rescale the weight of the different components. And this is done again through our query operation. So query work directly on distribution. I stress this because different work consider different kind of conditioning. So our is this kind of conditioning specific to distributions. Now, another component that we need to keep in mind is that we have a higher order function. So like in the example of Monte Carlo, we want to work with a parameterized function, parameterized by some function itself. So in this case, we had our function h, which we want to reason about. And also more in general, we use likelihood function. So in general, we want really to be in the realm of higher order. And also, we want to deal with the recursion. And as I said before, we assume some termination here. So we assume that we have some predicate terminate that prove a termination for our program. Again, this is orthogonal to my presentation, so I will not go more into this, although finding good method to prove, especially probabilistic program terminating, and especially higher order probabilistic program terminating, may be non-trivial. Okay, so this was an overview of the grammar. Now I want to go more into the free layer of our framework. So, but first, maybe let me spend a few words. So the requirement I said before, so that we have probabilities, conditioning, and higher order, and also probabilistic distribution over the real, make the setting quite difficult to reason about, because as some of you know, already finding a semantics for this kind of setting took a good semantic took quite a while. But now we have several semantics that have been proposed. And as I said in the introduction, we will base our work on quasi-Borel space semantics. So I want to stress this point because it was a non-trivial step that gave us the opportunity to look into this framework. But now let me focus on the three different layers. So as I said, the base of our system is an assertion logic. And we can think about this assertion logic mainly as a proving judgment of this form. We have a precondition, a term variable context gamma, and the postcondition. You can think about pre and post as logical formulas over variable that are stored in gamma. But remember that we want to reason about statistical property like the one I show you in the introduction. So what we will have in this assertion logic now are formulas that come from this grammar, which is a kind of a standard first order logic over some basic predicate. But the basic predicate are talking about are where the power of this assertion logic lies. So in particular, we are interested in a set of enriched expression which contain expression for expectation of functions, and then expression for talking about scaling and normalized distribution. So you can think about the last two to reason about conditioning, and the one for expectation for reasoning more in general about processes like Monte Carlo. What we may have assertion like the following. So we can have a judgment like the first one that you see here, where we are interested in the expected value of some function x, and we require that this expected value is less than 1. We may have equalities like the one you see on the second row, where we say that the probability of E prime, sorry, I think is the probability of E, the prime is not there. Oh, no, sorry. I got confused by my own notation. So suppose that x may appear free in E prime, so the probability of E prime given x sample from another expression E is equal to the expectation of still X taken from E, or for another expression like if A prime then 1 else 0. This is the correspondence between probability and expectation. Is a classical formula that we can use. The third is a formula for variance and so on. So we can define by this, the main point I want to make here is that by our assertion logic, it's true that we reason about expectation, but we can reason also about probability and other property like variance through these through equalities like the one you see here. What we have in addition in the assertion logic also to validate equalities like the one I showed you before are basic equalities on enriched expressions. So as an example, we have that we know that we have linearity of expectation, so we will have equation for linearity of expectation also in our assertion logic. We also have assertion that mainly make sure that the expectation integrate well with the other construction of programs like binary or the other monadic construction. And we have also some other equalities for probabilities. So for instance, we can define a query of an expression E1 in an expression E2 as a normalize of scale E1, E2. So all these are validated actually in the quasi-Borel space semantics that I mentioned before. And we integrate them in our logic as axioms. Now, an important point is that we are not aiming here to have a minimal complete set of axioms, but we have a more practical take, and we add the axiom that we need for our examples, more or less. Or to be more specific, we take a set of examples that we think they are representative of what one is interested to reason about, and we try to integrate axiom for this example. And we believe that these axioms are general enough for reasoning about several applications. Now, the last part on assertion logic that I want to mention is that we also add the domain-specific axioms like Markov inequality and Chebyshev inequality. These are used everywhere we want to reason about statement like the one I show you at the beginning of my talk. So probabilistic and quantitative statement. Markov inequality, Chebyshev inequalities are really fundamental in this setting. And one can imagine that, so for reasoning about accuracy of differential privacy, often is common to use other inequalities like Zuma inequality or Chernoff inequality, and one can also add them or perhaps can derive them as well. For instance, Chernoff is derivable just by Markov, I believe. Okay, any question on the basic logic? All right, so let me move to the unary system. Now, the main difference is that we have, before we didn't have a program, now we have a program P. The rest is the same. So we have a precondition, our context gamma, and postcondition. So previously we had the programs in the pre and postcondition, but now we have one specific program P that is in the judgment. Okay, so you can think about this as of a judgment as something like this. We have a precondition, we have a context. Sorry, here I think I switch where the context is and where the precondition is. Sorry about that. We have a program that, again, you can think about it as simply well-typed in a simply type PCF, and mainly we require this to be well-typed in the context gamma and having a type tau. And then we have a postcondition, and in this postcondition, there is a special variable R of type tau, which capture the output. So R mainly in phi stand for the result of evaluating E. Now, let me give you some proof rule. I hope they will not be too much, but and you don't need to read all of them in detail. I want to give you a flavor of what kind of rule we have in this unary system. So the first rule, we use UPL to say the unary system. So the first rule is the rule for application, and you can think about this as a dependent application in like independent types. So we assume that T as a postcondition or a type as for all x phi1 implies phi, where we replace R in phi with R of x. Then if we have that U can prove phi prime, then we can prove the conclusion where we replace U to x. So the R now is still in phi, but we replace U with x. So this is the dependent part. In general, we also have subtyping, which is important because is the connection, and you see this in the second rule, is the connection between our unary system and the underlying logic. So what is the V-PL is the underlying logic, while, as I said, V-UPL is the unary system. So here we can use arbitrary formulas of that we can prove in the underlying logic. So you can think about our system as trying to use as much as possible the structure of the type of the term T to guide the verification. And when we cannot use the structure of T, we can always rely on the underlying logic. This is a principle that we use in design our system. We have also rule for a specific construct like a query. Now this rule may seem a bit complex at first, but is actually a very semantic rule. You can mainly see it in the third row of the assumption, which is the postcondition for E prime. Mainly we require query to be well behaved, and we just take the semantic of query to reason about itself. So in some sense, this rule is what one would expect, but is not very useful in general because it's too general. So what we also did was to identify some domain-specific rule, where, for instance, one can use a more specific rule where we talk about the probabilities of running a query. So in particular, we talk about the conditional distribution. So in other terms, this rule represents Bayesian update or Bayes theorem. So we can use this kind of rule, which are more specific than what I showed you before. I should say, sorry, that I cannot really see the chat well because I don't know where my mouse is and I cannot scroll down in the chat. So if I'm missing a question, just it's better if somebody just
I'll
speak
check
up.
now, Marco, and if there's something, I'll let you know. So far, nothing, so you're okay.
Yeah, okay, perfect. Thanks. All right. So let's see again an example. So this is the example I gave you at the beginning, one of the example I gave you at the beginning, where we have the distribution on the left. We want to condition it with the filter that say that x and y need to be less than 1/2, and we obtain the distribution on the right. Now, something we can prove about our program. So first, our program now has this shape, is a query of two uniform distribution, in particular of a product distribution that is built out of two uniform distribution. And we query it by this predicate, lambda xy, if x less than 0.5 and y less than 0.5, then 1, else 0. You can think about this as an indicator function or as a filter. And sorry, an indicator function or a filter. And the type of this program will be just a monadic type over two real. So a distribution over two reals, of a pair of reals. And what we can prove is something like the following, that the probability that when we take a Z sample from R, that if we project the first value, so we take the first component, the probability that this is strictly less than 1/2 is 2/3. Mainly we are just projecting, as you can see in the picture on the bottom, we are just projecting to have x less than 1/2. So we are just taking mainly these two areas under 1/2. Okay. Now we can reason about this kind of property in our type system, but more interesting, we can reason about property like the one I showed you before about Monte Carlo. So again, Monte Carlo, we want to estimate the expectation, and we are interested in a formula like the one I showed you before, which mainly express the convergence of the process. And we can express this in our type system, and we can prove this. And the proof mainly boils down to a induction over function MC, so over our program. And mainly we do induction over MC, we do case, and then when we are in the branch, in the else branch, at some point we use a Chebyshev inequality to prove that we have this invariant that you see on the left. Okay. Now I will not show the whole proof here, of course, but you can see it in the paper if you are interested. Now, let me go into the relational system. Also, Katya, sorry, I should have asked this before. Am I supposed to finish by 10 or 55?
Oh, it's okay. You have about 9-10 minutes. So we started about 1 minute late. So you have 10 minutes. Okay.
And then I can take question after.
Yeah, if it's okay with everyone. Yeah, I think so.
Okay, perfect. So the relational system is very similar to the unary system, except that now we have two programs, E1 and E2, or P1, P2. And precondition and postcondition now can be thought about as a relation. So in particular, now we will have in the postcondition two special variables for the output of programs, R1 and R2. Again, we have a rule similar to the previous one. I will not go in detail here. The first rule is application. for this relational logic, what I want to stress is that we have application both for the first program and the second program. So these two programs have the same structure, top-level structure. So both are application. You can see it in the conclusion. We have T1 U1 and T2 U2. The rule is very similar. Is the generalization of the unary I showed you before is still dependent. There is nothing very special about this. Now, the second rule is again subtyping. And again, I want to stress that we can use the underlying logic in subtyping. Now, we don't have only rule for a program that they have the top level, they have the same shape at the top level. We can also reason about programs that have different shape. So here you have an example of a rule that allows us to reason about a bind, a program that has the shape of a bind, and some arbitrary E2. And these are very general to, very useful for really reason about arbitrary programs. Now, through this kind of relational logic, we can try to reason about a pair of two run of Monte Carlo. And we can prove something like I showed you before, where again, we have a probabilistic statement that talks about the result of the computation. And again, this can be proved by induction of the structure of the two programs. And in some particular point, we will use some assumption again, like Chebyshev inequality and Markov. Again, I will not go into the detail of this, but if you are interested, are in our paper. So trying to give you a bit more detail about what we have. So our system, this PPV, is built more or less on two ideas. One, a syntax that comes from some of our previous work on relational higher order logic, and the semantics on quasi-Borel spaces that I already mentioned before. What we do is that we introduce new structure at the syntactic level, and we introduce predicate over quasi-Borel spaces to interpret property of our probabilistic programs. The soundness of our system is mainly built in a way that I find quite interesting. So first, the soundness of the assertion logic, as I mentioned already before, is based on QBS, so quasi-Borel spaces. We validate the different axiom in QBS, and we can then use these for the rest of the reasoning. But also we prove soundness by then showing equiderivability between the level, between the unary logic, the unary system, and the underlying logic, and between the relational system and the underlying logic. So what this soundness tell us is that mainly the two layers that I show, so the yellow and the green, do not add power, do not add expressive power in terms of reasoning, because everything we can reason about in the underlying logic can be reasoned about also in these two systems. But what these two systems give us is a way of verifying program which is guided by the structure of the program P or the two program P1 and P2. And mainly a more general way to reason about our programs. Now, to conclude, I hope that what I show you convinced you that we can reason about complex property of probabilistic programs using tools that come from standard programming languages like type system or program logics. And we try to consider properties that are really of interest for the field. In particular, if you look at the paper, there is an interesting proof of the convergence of importance sampling. Importance sampling is a widely spread algorithm, and we actually verify the convergence of importance sampling with a dependency on the sample size, which is used often in practice, but that also was resolved only a few years ago. So I think that we base our work on a paper from 2015. So we are able to integrate quite a recent work and quite useful and practical result. Now, something we learn doing this work is that we need to design good domain-specific rules, and this is where the novelty of our work really is. So try to understand what are the basic principles that we can use to reason about this application we have in mind. Now, something we didn't do is to look at more interesting inference properties or algorithm, in the sense we didn't look, for instance, at some of these variational inference algorithm. It would be interesting to do it in the future. Now, something I didn't put on my slide, but I started with the motivation of using this logic to reasoning about private machine learning. We didn't get there, although we have a path to get there, but it's something we didn't do yet, and I hope we will do it soon. And with this, I conclude, and thank you for your attention.
Marco, thanks a lot for your talk. That's great. Do you people have questions?
Let me just do this.
So yeah, if you unshare, then maybe we'll be all able to see faces in the usual gallery view. Right. So yeah, I have a question. So is it just privacy of machine learning models you can do with this approach, or can it be, say, verification of machine learning models?
No, definitely verification of machine learning. Actually, the example we give are in the paper mostly are not about privacy, so are really about more. I think that the main point is that they are all not all, but most of the property are convergence property. So you can think about this as when your learning will converge, or to what your learning will converge to. I think this is an important way of thinking about machine learning properties, because we are really interested in quantitative statement of how close we will get to what we want to learn.
Okay. So in machine learning, we essentially deal with two things, right? There is an algorithm that helps us to train, say, suppose a neural network. There is an algorithm, say, regression, that helps us to converge to certain weights. We can verify the algorithm, or we could say, well, we don't care about the algorithm, but once I get the model, that neural network, I want to verify its properties that with certain probability, if its input satisfies certain property, then its output satisfies certain property. Which of these two things are closer here?
Yeah, very good. I should have been more specific about this. So for most of the component I'm thinking about, I'm not thinking about a neural network, but I'm thinking about other learning processes, like for instance, Bayesian inference, or for instance, even just some regression task, or
that's
some.
Okay. That doesn't matter. So let's say it's BiasNet rather than neural net. That's fine.
Yeah, and so these are the kind of processes we are interested into, like what is, so the algorithm is really so let me take a concrete example. Let's say a regression. I'm interested in the convergence of a regression to the true value. So this is what I'm interested into.
So yeah, it is really property of the algorithm rather than the linear classifier that you get at the end of regression.
Yes, because we work on programs. Yes, although the statement that we give is a property of the output of the algorithm. So, I mean, it's just a bit tricky to
a program
separate.
a program is a general word, right? So I could say this linear classifier is a function, therefore it's a program, and I want to prove something about this linear classifier seen as a function of n variables. But I could also talk about the regression algorithm and its properties that I run on the linear classifier. Anyway, but I understand it's more of the regression algorithm that you'll be reasoning about rather than the linear classifier that results from it.
No, actually, I would say that is more about the linear classified that we get whose description is provided by the algorithm.
Okay.
So it's not an ideal classifier, but is the one produced by this specific algorithm that we reason about.
In which case, that's very close to what people do in neural net verification. They also reason not about, say, backpropagation algorithm, but about the neural net that they get at the end.
Okay.
So I'll let others ask. I'll stop asking questions. I have more, but I'll probably call you again, Marco.
Sure.
Okay, team. You can at least switch on your cameras so that we could see you, and I'll stop recording if that baffles you.
I see your hand raised now. Sorry, I don't know if it was before.
Sorry, what is it?
Yeah, I have a question. Thanks. So, as you say, somehow half the magic is in the domain-specific reasoning, right? Every time you look at a specific example, you kind of have to come up almost from scratch as to somehow the predicates you need in order to prove it. So is there anything you couldn't do, like something that was really hard or fiddly or challenging? And if so, what was it?
So let me first comment on the domain-specific rule. So it's true that, as you said, like the magic is there, but it's also true that if you think about, especially, let's say the community I know the most is learning theory people, so a bit more theoretical machine learning people. They don't use an infinite array of techniques. They actually use a quite finite array of techniques and of principles. So like, as I said, the Chebyshev inequality and Markov inequality are everywhere. Chernoff bound is everywhere. Azuma inequality, they use it if they have martingales, and so on. So what we tried to do was to simulate a bit what they do on paper, in the sense of try to add this kind of main principle that they use and then support their reasoning in a mechanical way through our system. So in this sense, I think it's true that the secret is there, but I have the hope that we can reasonably build some system that support most of the practical property that one want to reason about. Now, what we didn't do, so yes, there is definitely something we wanted to do and we gave up in the end. I need to remember. There was one specific thing that we were not able to do. So first of all, I think two I can mention, if I remember. So the first that I remember is reasoning about convergence of Bayesian learning. So this is tricky. It's very tricky, actually, in the sense that the methods that go into these are quite hairy and quite difficult to manage, even on paper, not only mechanically. So even on paper, it's difficult to reason about Bayesian update in a convergent sense. And there are only few results about this. So we tried to take some of the few results, but we were not able to really do them in a meaningful way, meaning from principle. So we could add them, but it's not very interesting. So doing them from basic principle was not easy. The second one was some convergence algorithm, some sampling algorithm, but now I have to say, I don't remember which one was it. But some, again, some sampling algorithm, we were not able to reason about this because it requires a bit of a kind of reasoning that the only way we were seeing to do it was to add it as a black box, but it defeats a bit the purpose then of having it in a logic, because then you are just adding it as an axiom.
Yeah, I mean, even to give you like a more encouragement, I guess, right? Even if we're taking away the probabilities and we're looking at optimizing or compiling a deterministic language program, right? Proving in general that some of the performance has improved is actually very difficult anyway, right? So add probabilities is just becoming even harder. So it's not a, kind of an encouragement that this is challenging. So
yeah,
thanks.
Thank you.
Under more questions, Marco, is it implemented in a way that we could play with, or is it implemented as a prototype only?
Yeah, it's implemented as let me say, it's half implemented as a prototype, in the sense that, so as I said, that this was mostly the work of Tetsuya, who was a postdoc with me, but is not as keen to implement what he does. He find more fun to do the math behind. And so, although I started, we didn't finish.
Mm-hmm. Okay.
Hi, I just have, I'm not have a question, but I have something observed in our experimental on machine learning. So just want to share the things we might to you. So the things is that we train a neural network model, right? So we train it for 100 times, but we got a very slightly different trained models for in each times. And then we use each model to do some prediction, but the prediction, it seems it's a bit a distribution. So so I just want to ask something, maybe some probability in the neural network, in the model, machine learning model. I mean, so I think I just wonder, how do you think about this phenomenon? Yeah. So
yeah, so
okay.
That's a very good question. So I think that, as I said, when I think about our work, I don't think about a neural network. So I think a neural network have a different aspect that make them particularly challenging. And the aspect is that they are really...
yeah. So yeah. So
for me... Sorry, just one thought. So part of the challenge is that the result of the neural network depends very much on the data. So mainly in our work, we assume more or less that the data, we know the shape of the data, but we don't assume too much about the data. So you can think about what we do as a kind of a data dependence. So the probability come more from the algorithm itself and not from the data, as I was saying before, except in some specific cases. And this makes mainly reasoning easier for sure, because everything is in your program and not in your data. So I think this is the main challenge to deal with a neural network, is having a good way to represent data, which is not trivial.
Yeah. Okay. Thank you. Yeah. Yeah. Yeah.
There is, just to say, there is some research in machine learning that works with data that was artificially generated and has a known distribution. So, yeah.
Yeah, indeed. So you could use some description of the data, which give you the data generating process. And this is an interesting thing we didn't do, indeed.
Yeah. So yeah, in my perspective, yeah. So one thing is that the data is not very good, because there may be some correlation between the data side, and we should make sure that no correlations. Yeah. So another thing is, I think in neural network, the first one is the weight. Initial weight is random generated, and second one is drop off probability. You also have a random factors in it. So this all cause the training result is differ from one to one.
Yeah.
Okay, so we're now really almost quarter past the hour. Just final call for any questions if there is someone who wants to ask. Right. Well, Marco, thanks a lot. It gives us a lot to think about. We're just at the start of the project, and we are still thinking hard how to even start it properly. So that was really inspiring.
Thank you very much for the invitation, and I hope I will have an invitation also for when the travel, when we will go back to travel, because I miss Scotland.
Oh, you're not just hope, you're a project partner, so you should insist on it. You should email me as soon as the first airplane goes from the US to Scotland saying, you know, where is my budget? And so you're completely entitled to it. So we're looking forward to seeing you with us very soon then. Okay.
Great. Thank you again for the invitation.
Thanks. Thanks again for coming. Bye-bye.
Bye.